Okay, welcome everyone to the probability and analysis webinar. So today's speaker is Joao Ramos. He's going to talk about time frequency operators, localization, and their eigenvalues.
Thanks, Polona, for the introduction. Thank you, for the organizers for inviting me for this talk. And just before I start, so maybe as there are some people with background in classical harmonic analysis, this is not the kind of time frequency analysis you're expecting, right? So that's slightly different. So yeah, but well, without further ado, let's maybe go into it, and you're going to see what I mean. It is completely related to stuff, for instance, the classical, that yields the classical solution to Carlson's, the Carlson's theorem, and so on, and bilinear Hilbert transform, but it is not the exact same thing. So let's start with with a naive definition of the Fourier transform. So we're going to normalize the Fourier transform with e to the minus 2 pi I t psi. For a function in L1, this is well defined. And the first question that we will try to analyze, it's going to motivate our problems today, is a problem of retrieving a function from, I don't know, information on the space and on frequency. That is information on f and f hat. So the first example that you can see on the screen is if we have complete knowledge of f hat and we use for inversion, then we get f back again. But that is, for certain classes of functions, that is a little bit too much, because, for instance, if you know a priori that f hat has compact support, an interval minus 1/2, 1/2, then we can recover f from its values at integers, because f is going to be an analytic function. It's a well understood theory. It's the Shannon-Whittaker formula in in signal processing and so on. The third example is actually a very recent topic, one topic that I'm very fond of, which is, well, if f is even and actually belongs to the Schwartz class, then we can recover f from its values at root of n and the values of Fourier transforms at root of n. Right, this was proven by Danilo Radchenko and Marina Wiazowska a couple of years ago. Its proof is very beautiful. It's a consequence of the circle of techniques that arises from the sphere packing problem, but that's a story for another time. For now, let's focus maybe on, well, all these formulas have on the following fact. We have to focus on the fact that all of these formulas, they can kind of give us some information that is the values of f and the values of f hat and so on. Given these two certain sets of data alone, we can recover f or f hat or something like that, but we cannot recover some more intrinsic properties that are more difficult to quantify by just looking at the signal f or its Fourier transform. So in the words of Karl-Heinz Gröchenig, so you can think of f as a piece of music. So f itself is a temporal behavior of the signal. And you can kind of, well, by looking at f, you can basically detect a little bit of rhythmical patterns and so on and so forth, but you cannot tell so much about the key or the melody of this piece of music by just looking at the temporal behavior. On the other hand, if you look at the dominating frequency bands of the signal, you can, well, maybe you'll be able to recognize the key of that piece of music, but rhythm, well, that's going to be lost, and the melody, still, it's not going to be recovered. So although we may have information on f and f hat, neither of them show the relevant information actually that can be heard by the ear, because the ear, at every moment, it is kind of dissecting frequencies. It is looking also at the temporal, at what has happened in the last couple of seconds and so on. And it manages to distinguish different instruments, the key, and kind of get the sense of rhythm and pace and melody that we perceive. So it is kind of a joint information that is recovered from this time frequency information that we have, if you wish, that we call music. So in musical terms, a time frequency representation, it's basically what a musical score aims to represent. So you have kind of the behavior in time, and then you have also, well, how the different musical notes are playing out throughout the time and so on and so forth. So you're kind of playing out frequency and time at the same time, kind of in a Jordan representation. So what we want actually is with a given function to try to find a joint representation of that form of the function that kind of at the same time displays the behavior on the space and on the frequency side. So that is what we're just discussing. The first obstacle, which is the inserted principle, prohibits us from doing so in a sharp way, that is just cutting the function and then cutting on the Fourier space and concentrating absolutely, because, well, you cannot do that by the inserted principle. And the solution, as you see, is something that we call the short time Fourier transform, which does this kind of chopping things and regularizing and kind of concentrating on time and frequency with a little bit of noise still, but kind of in a good way. So what is that? So for a fixed function, which we're going to be calling the window function g, the short time Fourier transform with this window g is just the operator vg of f, which takes two arguments, x and psi. It's the integral of f of t, g of t minus x bar, e to the minus 2 pi I t psi. So we immediately see that if g is identically 1, we recover the usual Fourier transform. And, well, as you can think of g as kind of a bump, and this parameter x that we're putting there is just taking this frame of reference which the function g provides, which is a bump, and shifts this frame of reference around. So for each given x, we're shifting the frame of reference according to x, and then we're taking it for a transform. And that is more or less what's represented in this picture. So I'm sorry for the resolution of that, but basically if you have a signal x of t and a window g of t, which is this bump that I'm showing on the screen, basically what the short time Fourier transform is doing, well, we're shifting this window, this frame of reference around, and then we're taking Fourier transforms. And then we get each section as a Fourier transform of these shifted localized versions of the signal. Yeah. So let's maybe discuss a couple of properties of the short time Fourier transform, right? So first of all, it satisfies that if you take in a product of v with a certain window g1 at a function f1 and v a certain window g2 and a function f2, then they actually tensorize. So in particular, if g1 is equal to d2 and the modulus, so the L2 norm of them is equal to 1, then this full short time Fourier transform with that fixed window is going to be an isometry from L2 of the real line to L2 of R2. Another nice property of the short time Fourier transform is that, well, you can recover f from its short time Fourier transform by just an inverting formula. So basically, well, this is a well-known idea in the other neighboring field of time frequency analysis. This time, that field where it's directly related to the proof of the Carlson theorem and so on. But basically, the idea is, well, you get this operator which has some symmetries. So the symmetries of this operator are with translations both in x and in psi. And, well, if you want to recover f, it's not a bad idea to average over the group of symmetries of this operator. So that is basically what's being done in this formula. And finally, so there is an uncertainty principle for this operator. So if f and g are in L2 with L2 norm 1, and the integral over u of vg of f squared is at least 1 minus epsilon, then the measure of u is at least 1 minus epsilon as well. And the proof of that is actually really simple. All we have to do is notice that from the definition of the short time Fourier transform, this inequality holds. So pointwise vg of f is less than L2 norm of f times L2 norm of d, which is 1 by assumption. And so this inequality follows just by, well, passing the absolute value inside if you wish. And then the question that naturally comes from such an inequality, well, if one wants to be very precise about uncertainty principle, because sometimes we like to be precise about uncertainty principle, see for instance, well, Hardy's uncertainty principle, which we can quantify exactly what the variance of the Gaussian is, the optimal variances of the Gaussians are, so that a function and its Fourier transform cannot decay faster than the Gaussian. So it's a natural question to ask, well, is this bound on the set U optimal in a certain sense? So if I have this bound that the integral of the short time Fourier transform squared over U is at least 1 minus epsilon, is the measure of U at least, well, can we find an example of a U with measure equal to 1 minus epsilon or very close? And well, actually, so just quickly on that, so there is a first improvement of that, which was by Elliott Lieb first, by using the Sharp-Hausdorff-Young inequality. He could obtain that the measure of U is at least 2 times 1 minus epsilon squared. With epsilon small, this is better than the other thing, but still conjectured not to be optimal for general windows, and well, basically the heuristics are, well, the concentration shouldn't be for any window, reasonable window, the short time Fourier transform shouldn't allow for concentration, for absolute concentration or almost absolute concentration on a certain set. It has to have a lot of loss. And the first step in this direction of confirming this heuristics was given by Fabio Nicola and Paolo Tilling last year, in a beautiful paper where they analyzed the case of the Gaussian window. So if phi, or the G in the previous slides, is a Gaussian normalized in L2, then well, if the integral of U over U of the V phi of f squared is at least 1 minus epsilon, then we have that the measure of U is at least log of 1 over epsilon with equality if and only if U is above. And I see on the chat that yeah, there's a little bit of a discussion of a reasonable window what a reasonable window is. I can give a brief answer on that quickly. So yeah, something that is, I don't know, let's say that doesn't look, that is quite regular, that it belongs to the Schwartz class whose variation is small or something like that, and something along those lines. So for instance, you can take an L2 function, expand in its Hermite basis. Let's say that, well, reasonable functions, or let's look at the toy model. So let's look at windows which are finite combinations of Hermite functions or something like that. This is a first class of windows which would be of interest to in this problem, right? And the first Hermite function is the Gaussian. So that's basically the motivation of Fabio and Paolo in this result. Okay, so the strategy of proof and their results. So I'm going to go quickly over that because we're going to be seeing this very shortly again. So if you take a Gaussian, then the short time Fourier transform actually, it is directly related to an object called the Bargmann transform. So you could define BF of that being this transform, which is on the screen. Then actually the short time Fourier transform with phi as a window, it can be written as a certain modulation times BF of z times this e to the minus pi z squared factor, basically, or b pi z squared over 2. So you can translate the problem of finding the optimal sets for the Gaussian window to finding the optimal sets for concentration of the Bargmann transform. And the Bargmann transform actually has this nice property that it takes, it is an isometric isomorphism between L2 and this space of functions on C, which have order 2, and such that this integral over C of f squared e to the minus pi z squared is finite. So we have to optimize something on a that's related to complex analysis now. So that's the first translation of the problem. The second as well, there's this supremum there that we can exchange the order, right? The supremum over the measure of u and the supremum over the norm of f equals 1. So if we exchange the order, so first we take supremum on the measure of u, then we see that we can take the level sets, we can take the optimal sets to be of the form of a level set of this function u of z, where u of z is just this function being integrated modulus of f of z squared times e to the minus pi z squared. And well, what do these level sets look like? They have to be of the form u greater than u star of s, where u star of s is just the decreasing radial rearrangement of u, right? Which has this property, this measure theoretical property. And finally, just very quickly, I'm going to be explaining this again, but the idea is to find some convexity property on this function I of s. So its derivative is u star. That can be easily seen. And its second derivative is this integral right there. So by using Cauchy-Schwarz, the isoperimetric inequality, and the fact that the function u, this is a very crucial point, that log of u, if you take its Laplacian is -1, then one can prove, and I'm going to show you very soon how, in a different context, that I prime prime plus I prime is actually greater than or equal to 0. If you play around with this one-dimensional convexity a little bit, you can get to the conclusion that this function I of s has to be at most 1 minus e to the minus s for any s greater than or equal to 0. And yeah, so some open questions in that regard are, for instance, what happens for the windows? For instance, if g, as I was saying, is a finite sum of Hermite functions, can we obtain some result, even if not sharp, better than Leibniz uncertainty principle? That's still open as far as I know. That hasn't been tackled, and these techniques here, they open the door for this problem, for this kind of partial progress. The second question is, what happens if there is an almost equality in that theorem above? Can we say that we are close to a disk? And I forgot to mention that there's actually an ongoing work with Paolo Tidi and a master student of mine here in Zurich, where we're addressing this question in a very basic setting. And the proof above, so the final thing that I would like to get to is that the proof above uses several, heavily analytic elements from geometric measure theory and calculus of variations. Can one find a purely variational proof of this result? So in which sense? That, well, instead of kind of characterizing by inequalities itself what the extremizer looks like, trying to come up with a more variational proof in the sense of, well, take a sequence of almost extremizers. Can we prove that it converges in a certain sense to an extremizer of the problem? Can we then prove that this extremizer, by some underlying geometric feature of the problem, has to improve itself and then become a ball or something like that? So can one find a proof like that? And well, this is my personal take on this, but if there is a proof like that, then it should help in these two problems above. So in a certain way, it should make things a little bit clearer. Although this previous proof is so ingenious and brings together so many things that I think that any purely variational proof would be at least hard to conceive at the moment. So finally, well, we get to the first topic in which I would like to say a couple of words of my own contribution on that. So besides the short time Fourier transform, there are other ways to measure and do this localization procedure that I was trying to explain in the beginning, right? So as I said, the short time Fourier transform, it has two nice symmetries, which is translation in space and translation in frequency. And if you impose these two symmetries, basically the short time Fourier transform is the natural operator to consider. Or, well, there is a more representation theoretical background on that, or basically this is kind of a representation associated with this group of translations on R2 or something like that, but let's not dive so deep into that. But then, well, if you, instead of taking a look at the real line with translations and then on the Fourier side translations again, let's maybe look at, well, let's suppose that I want to keep translations on space as a, I don't know, as a symmetry, and then dilations on the frequency as another symmetry. And there is an operator that relates these two that does the job for us, and this operator is the wavelet transform, the continuous wavelet transform, which is WG of F, again, two arguments, but right now the argument, oh sorry, this should be WGF of X and S. And the parameter S has to be positive, so it doesn't live on R2 anymore, it lives on R cross R plus. And it's just this convolution of an L2 normalized version. So it's dilated in L2 by S. So you take G, you adjust the frame, but then before adjusting the frame, you actually take a certain L2 of dilation that preserves L2 norm of G according to S, and then you start adjusting the frame and start taking a look at what this operator yields. So then, just like well, in analogy to the short time Fourier transform case, there are some kind of orthogonality properties. Like for instance, if you take inner product, but right now, well, it's not the inner product on L2 over R2, it's with respect to this hyperbolic measure dx ds over s squared, then you have a tensorization again. Well, you still have F1 and F2 inner product in the Hardy space, but then you're going to have the inner product of G1 hat and G2 hat on L2 of the positive real line with hard measure dt over t. So in particular, if this quantity, this L2 norm with respect to the hard measure on the positive real line of the Fourier transform of G is 1, then this wavelet transform is an isometry from the Hardy space to the upper half space with hyperbolic measure. So we have a very similar context in comparison to the short time Fourier transform case. And moreover, you can also invert it with a formula of averaging basically over groups of symmetries, as I said before. So let's not dive so much, let's not dive deep into that either. But then what I would like to show you, just to reinforce this idea that the wavelet transform is a little GIF with this property that I was saying. We first dilate, and then we kind of move the frame and take a look at what this integral gives us. And this is going to yield some representation of the function as a result of that. It's quite different from the short time Fourier transform case. So you see that the dilations kind of play a massive role in that. They detect a lot in the beginning, and then they start being so sensitive in the end, but they still get a little bit about the peaks in the of the function. But yeah, it's just more of a matter of curiosity, this picture that I wanted to show. So yeah, so an analogy, so the last question that we haven't still analyzed that has an analog between the short time Fourier transform case and the wavelet transform is the uncertainty principle. So if you do the same computations that we did for the short time Fourier transform case to the wavelet case, we're going to get that, well, if you take a subset of the upper half space U, and suppose that the wavelet transform with window G applied at F, it concentrates in the L2 sense at least 1 minus epsilon at U, L2 norm of F and L2 norm of G are 1. Then what we have is that this time not the Euclidean measure, but the hyperbolic measure of U is at least 1 minus epsilon. And we can ask again the same questions. Is this result sharp? What else can be said about this result? Is there a special class of windows, just like in the other result, that we should look first to try to get the solution of this problem? And yeah, so answering this last question, the answer is, well, there is a natural class to consider, which is this class of functions psi beta, which are, if I'm not mistaken, the Cauchy wavelets. Just that, well, you just define them so that psi beta hat is 1 over some constant times the function t to the beta e to the minus t, but only truncated on the positive real line so that it belongs to a Hardy space. And this c beta constant normalizes it in L2. We're going to be seeing in a while why these functions, these windows are special. So bear with me for a bit. With these windows, we have, so this is a result of mine with Paulo Tilly that has been, well, we put it on, we uploaded it to archive a couple of months ago. So for any beta greater than 0, if you pick any of those windows, then we can say exactly what are the optimizers of the concentration problem. So if the wavelet transform with window psi beta concentrates optimally at a certain set U, then, and you fix the measure, the hyperbolic measure of the set, then the set has to be a pseudo-hyperbolic disk, which, well, coincides with a Euclidean disk, but the center and the radius are going to be different between when you change from one context to the next. And well, by computing the constants explicitly, you can obtain a lower bound on the measure of that set, on the hyperbolic measure of the set U, in case you know that the concentration is at least 1 minus epsilon. So if the concentration of a certain over a certain set with respect to these windows psi beta bar is at least 1 minus epsilon, then we know that the measure has to be at least pi times 1 over epsilon to the 1 over 2 beta minus 1. And I'd like to discuss a little bit on the proof. And well, as in the previous case, the windows, they actually played the decisive role because, well, if you recall, the Gaussian had the nice property that the Bargman transform takes L2 of the real line into a space of analytic functions on C. Right now, our windows have this very nice property that basically they take, after, well, a couple of changes of variable, they take L2, well, the Hardy space of the real line, into a Bragman space on the disk, which is a space of analytic functions f, such that this integral on display is finite. And yeah, so then we just have to, well, by translating from one context to the next, we have to optimize this quantity, so this integral over omega on the for f on the Bragman space. If you know that, well, the hyperbolic measure of the set omega is fixed to be s, and f is an arbitrary function in the Bragman space. So we got our first parallel. Let's see what happens next, if there is any further parallels in this context. So just like in the previous case, call this function v of z just the modulus of f squared times 1 minus modulus of z squared to the alpha. And doing the previous trick of exchanging the order of the soup, we have to maximize this function j of s. So this is the integral on the super level set of v of the function v, where you define this v double star as a certain hyperbolic rearrangement. So it's just, well, that's a fancy word for saying the unique function that satisfies this property here, right? That the measure of the set where v is greater than v star star of s is equal to s. So, as in the previous case, and right now I'm going to explain more or less what the techniques are going into the proof of the short time Fourier transform case. So, as in that case, we see that we want to get some convexity for j. And first of all, j prime is v star star of s. That can be easily computed. And j double prime is this weird integral. So what is this integral? Well, you might think it's not nice. It's it's ugly, but it has a nice property. So if you use Cauchy-Schwarz, if you take this minus this integral to the -1, that is just the integral itself, and multiply by this other integral on screen, using Cauchy-Schwarz, you get this integral over v over the surface where, or the curve where v equals v star star of s, 1 minus z squared to the -1. And, well, by the isoperimetric inequality on the hyperbolic disk, on the other hand, this last quantity on the right is at least 4 pi s plus s4 s squared, because this set where v, well, this was in the previous slide, the set where v is greater than v star star of s has hyperbolic measure equal to s. So we can use the hyperbolic isoperimetric inequality. We get a lower bound for that. Next step is, well, on the other hand, why is it interesting to use this integral over v equals v star star of the modulus of the gradient? Well, because we can integrate by parts, and we know what the Laplacian of log v looks like. The Laplacian of log v, because, well, the log v, as we said, is a product of an analytic function with something like 1 minus modulus of z squared to a power, then the Laplacian of log v is equal to this expression on screen, -4 alpha plus 2, 1 minus modulus z squared to the -2. So if we integrate by parts in this integral, then we get that the integral of this, of modulus of the gradient of v over v star star of s, this is going to be equal, actually. So there's a minus sign here. There's a slight a typo there, but it's going to be equal to -4 alpha plus 2s. Or I think it's actually 4 alpha plus 2s, but in any case, because of the minus sign mistake, sorry about that. So then, yeah, we get actually a way to compute this integral, and we got an explicit inequality with Cauchy-Schwarz, so we just have to bring it all together. So bringing it all together, we're going to get this inequality 1. So j prime of s is greater than this intermediate thing, which can be rewritten by the properties as minus alpha plus 2 j prime times something, some explicit function. So this is our convexity property. So now we compare this j with the function theta of s given by this. And this theta of s actually satisfies this inequality 1 with equality everywhere. So one just has to use like a maximum principle like argument, which in dimension 1 is very simple. And one obtains that j of s is less than or equal to theta of s for all s greater than or equal to 0. And actually this alone already proves the result, because this theta of s is exactly what you get when you plug in a circle, a disk in the concentration inequality. So then it just remains to analyze the case of equality. So equality holds for some s. If, well, there is equality here in 1 basically. So if you retrace all the steps, we have to have equality in the hyperbolic isoperimetric inequality, and that only happens if you are a hyperbolic disk, or, well, an Euclidean disk with a weird center and a weird radius. And then if you trace it all back, all level sets have to be like that, and then the function has to be of a certain specific kind as well, and we're done. So yeah, I'm getting to the last part of the talk. Just before we go into this, do we have any questions on the previous topics or something like that? So if I'm going too fast, also I can, if you have questions about something that appeared before, please ask me now. I'm glad to explain.
Would it be interesting to consider domains with different measure, like not a hyperbolic measure, like restriction?
Right. That's a very good question. We started actually looking at exactly this problem. So with not the hyperbolic measure, but the Lebesgue measure. And we found that actually it's very weird, because there are no extremisers in that case. And the extremisers, you can actually compute the constants explicitly, so the limits and all that. It behaves weirdly. Going in this direction, I think it would be an interesting problem to try to see if in a certain sense the hyperbolic measure is the only one for which the ball is the unique extremizer or something like that. I think this might even be true. I just don't know how to prove it yet, but I think it's a nice. This would be a nice question. All right. So if we don't have any more questions, I'll move on for now. Well, so let's look then at the question related to the circle of ideas we were discussing in concentration and localization. So first, well, up until this moment, we have studied how to maximize concentration if we are taking soups over all sets and all functions at the same time. So a crucial idea is that we're taking double soups, right, in this in all of the problems so far. However, if we fix a set and ask ourselves, well, what is the function that best concentrates in that set? One is, well, if one does a variation of approach on that, one is naturally led to an eigenvalue problem. So if you define this operator L of U to be Vg star indicator of U Vg, this is what we call the localization operator associated with the set U. Then the task of maximizing the integral over U of Vgf squared over all f who have L2 norm 1 for this fixed U is the same as finding the largest eigenvalue of this operator and the corresponding eigenfunction. So, well, in this area of time frequency representations, it's in signal processing and the applications thereof, it's kind of a pivotal problem to obtain information on U from information on the eigenfunctions and eigenvalues of these operators, and moreover trying to deduce as much information as possible on the set U with as little information as possible on the eigenfunctions and eigenvalues. And for instance, in the result by Fabio and Paulo, it shows that, well, if you take a window to be Gaussian, then the first eigenvalue is maximized if and only if U is a disk. If we consider the class of all sets with a certain measure, certain fixed Lebesgue measure U. Okay, so from now on, let's look actually at the particular case of the short time Fourier transform with the Gaussian window fixed, right? So the study of this operator was actually started by Dobeschi and Paul in 1988, where they proved that actually, well, they computed the spectrum of this localization operator with U being a disk explicitly, and the eigenfunctions as well. But then a natural question is whether there is an inverse problem associated with it. So if I give you a set and its localization operator, and I know that, well, all of its eigenfunctions are equal to Hermite functions, can I say that the operator is a disk itself? And this was actually proved in a much stronger result, and that was established by Abreu and Döfler in 2012. Or they proved that actually you only need one of the eigenfunctions to be a Hermite function in order to characterize the domain. So if these localization operators, they happen to have a Hermite function as an eigenfunction, and they are simply connected, that's very important in their proof, then the domain is a disk. And the question that, well, is very natural from this discussion is, well, if U is a domain, but if you don't know that it's simply connected, if you just know that it's connected, what can be said? Naturally, well, an annulus has the same property. One can do the same computation. An annulus has the same property as the disk in terms of its eigenfunctions. So the disk is no longer unique, but can we say that if the domain has an eigenfunction, which is a Hermite function, then the domain has to be radial or something like that. And moreover, can we find domains, non-trivial domains, that have a finite linear combination of Hermite functions as an eigenfunction to their localization operator? So if I give you, I don't know, a Gaussian plus epsilon times the first Hermite function, can I find a domain that has this as an eigenfunction of its time frequency localization operator? And so I'm going to give, so my last contribution I'd like to talk about in a couple of minutes is an answer to those questions. The first one kind of fully, and the second one partially. So suppose a set U is multiply connected. So that is, it's connected but not simply connected. And that one of the eigenfunctions is a Hermite function, then U is an annulus. So this is our first result. And the second is actually a negative answer to this, is a positive answer to the second one. So if you take a function that is, well, basically this technical condition, you don't even need to read it. It just says that, well, it is a Gaussian, H0 is the Gaussian, right? F0 is H0 plus a perturbation, which is an allowed perturbation in terms of other Hermite functions. So it's a Gaussian plus some noise terms which are controlled well enough. Given that, then we can find a certain parameter lambda that depends on the coefficients, well, not on the coefficients, but on how big they are, such that for every value lambda below this threshold, there is a domain U of lambda, such that this function f naught is an eigenfunction of the localization operator of that domain with eigenvalue exactly equal to lambda. So we're finding no trivial domains with basically any arbitrary perturbation of a Gaussian as an eigenfunction. And these domains, of course, cannot be disks or anything. They have to look, I don't know, presumably very weird. So just before I finish, I'd like to give a couple of so these results, by the way, are in preparation. It's going to be taking a couple of months until they're out, but bear with me for a bit. So in a couple of months, they should be on archive. So the proof of them is just like, well, for the first result, we can still use the Bergman transform. And the Bergman transform has this nice property that, it takes the Gaussian into the function identically 1. It takes Hermite functions into multiples of z to the k, which is very nice. So if you take Bergman transforms in what it means to be an eigenfunction of the localization operator, you have to trust me on that one, but you get this integral equation, that the integral over u of z to the k, e to the pi w z bar, e to the times this measure, right, e to the minus pi z squared area measure is lambda w to the k. So if you differentiate k times in w, then you get actually, well, it's a nice trick because you get rid of the z to the k factor here, and you get rid of this w to the k on the right hand side. You just get a measure. The integral of the indicator of u against this measure with this kind of Fourier transform factor is equal to a constant. So, well, we take then a different perspective towards that. It's the same as looking at, well, if you take the indicator of u times modulus of z to the 2k times this Gaussian, and I subtract a certain constant times the delta, if I take its Fourier transform, so this is a compactly supported function, therefore it extends to C2 by the Paley-Wiener theorem. So the Fourier transform of that extends to C2 by the Paley-Wiener theorem. So what this equation is in the beginning is telling us is that the Fourier transform of that vanishes on that complex manifold where xi squared plus eta squared is 0. And a couple of computations actually with this fact shows that this is equivalent to the following. So there is a u complexly supported and continues on R2, such that Laplace u equals f of modulus of z, where f is, well, just this weight that is defined below, times the indicator of u minus constant times the delta. So this is kind of a standard thing. So basically, if the if the Fourier transform is vanishes on this complex manifold, we can basically invert it back and get a solution to this problem. So then we use a PDE approach. So there is this famous result in the 80s by Haranov, Schiffer, and Zalkman, where they say that basically if you have a solution to 2, and it is connected actually, and if the zero set of f is discrete, which is the case here, if you have a solution to 2, then U has to be an annulus. And then we're done. And just for a couple of minutes, let me briefly mention what the proof of the second theorem looks like. So if I take, basically I take my function f naught, let me go back a couple, which I want to prove it's an eigenfunction. If I take its Bargman transform, then it looks like this polynomial p of z. So again, by the condition on the Bargman transform, by using that with the eigenvalue condition with respect to the localization operator associated with U, I get this integral equation. Instead of differentiating on, k times on the same variable, I use this differential operator with respect to P. Basically, I govern my the way I'm going to differentiate things with respect to the polynomial I'm using. And denote this polynomial that I get by differentiating P with respect to itself by Q of W, so we get this new polynomial. And our new task is to find, if we find a U that satisfies this first integral equation, then it has to satisfy this one below. So that is our first task right now. Then we can use the same strategy as before. So, actually first, we use the theorem of Ivanov, which says that if the polynomial Q is very close in a certain sense, if its coefficients other than the first one are very small, then we can find a domain D with this property, that basically a certain Fourier transform over D is equal to a certain multiple of this polynomial Q. Okay, so instead of solving that integral equation, by using the Fourier transform method that I highlighted before, we have to solve a different PDE. And this PDE at this time is that the Laplace of U is modulus of P squared e to the minus pi modulus of that squared indicator of U minus a certain ratio of lambda and lambda naught indicator of D. So if the coefficients of P are small, then there is a large ball without zeros of P. And we may replace the function f by a suitable truncation, and the problem will essentially not change. So finally, if lambda 0 is sufficiently small compared to this lambda parameter we're setting, then this set D is going to be close to a ball. We can use a result of Gustafsson and Shah-Golian, which actually manages to find a solution to the previous truncated problem. And if we make lambda small enough, then we can also guarantee that this solution was actually a solution to the original problem, and we're done. So basically, as a quick recap, so both of the theorems went through kind of a, this is basically a free boundary problem, a global free boundary problem, but nonetheless a free boundary problem in their resolution, and both of them kind of use the explicit solutions and explicit constructions with respect to this PDE, to this free boundary problem, to get the result. And this solves our problem as desired. And just before I stop talking, I'd like to highlight a couple of final open questions. So are these conditions that the coefficients, that the perturbation is more needed? Maybe so, but actually, can we say that instead of it's a Gaussian plus a perturbation of something else, can we say that it's a fixed Hermite function, say H1 plus a perturbation of everything else? Can we kind of switch which is the leading term and which is the perturbation around? Because this proof only allows for the Gaussian, but maybe that's an unessential feature. So are the domains U lambda unique for each of the eigenfunctions? So Are they unique in a certain sense? So if I fix a lambda and an f0, is there a unique q lambda with that property? And can something else be said about the geometry of those domains? Are they, well, for instance, simply connected? I think they're going to be. One can probably prove that. But are they abundant in a sense? Are most domains like them? Or is this a rare property? Well, this is still to be quantified, and I don't know how to quantify that myself, but I think it could be an interesting problem to work next. But that's where I stop. And yeah, thank you guys for coming to the seminar.
Thank you, Joao.